grateful to her. So I'm Sam Rose. I'm a fourth year graduate student at Caltech, where I work with Monse Kozliwal. This work was done as part of the ZTF collaboration. So ZTF is a all-sky survey from Palomar Observatory, which does a lot of really great transient science, discovers many supernova, including 2017 EAW. And also on behalf of the Winter Collaborations, which is an infrared survey also located on Palomar Mountain. I'm going to talk about my favorite instrument on Mauna Kea, not for much longer. So Genevieve talked a little bit about dust formation. I just want to say a little bit like, why do we care about studying astronomical dust formation? There are a couple of reasons. The first is that star formation is dust obscured out to very, very high redshifts, out to at least redshift of 4, and definitely by cosmic noon at a redshift of 2. Dust formation is primarily obscured by dust. The kinds of stars that we are getting are formed in these giant molecular clouds, which maybe need dust in order to cool and collapse. If you want to understand something about stellar populations and stellar evolution of galaxies, you need to understand something about how dust forms. The second reason is that dust rocks, in that the things that form rocky planets like our own planet Earth are dust particles around these newborn stars, which condense and form into these rocky exoplanets. So if you want to understand why we can be astronomers and have places to put our telescope, you also need to understand how dust is forming. Genevieve also mentioned this, but we have now observations from James Webb Space Telescope of very high redshift galaxies out to redshifts of 8 and 9, where the age of the universe is only about 600 million years old, which show that dust is formed very early in these galaxies. We have evidence of UV bumps from polycyclic aromatic hydrocarbons, which are the smallest carbon-rich dust grains, as well as continuum features, which suggest that these galaxies are very rich in dust very early on, which is challenging for some models of dust formation, which rely on these low-mass AGB stars to form. Supernova, which of course come from the most massive stars, can start to form dust very, very soon after star formation. In the early universe, you should expect that dust formation from supernova explosion should dominate over these low-mass AGB stars, but the amount of dust formed in each supernova explosion is incredibly uncertain. And this is something that we need to continue to study and try to work out. I'll talk a little bit about the timeline of supernova dust formation. So I have here, in lieu of time, the electromagnetic spectrum, but it turns out they kind of approximate each other. At very early times, supernova are quite bright in the ultraviolet and the optical. So optical surveys like CTF now discover thousands of supernova per year regularly. You can do UV flash spectroscopy at very early times, which can show signatures of CSM interaction, which might indicate some kind of pre-existing dust around the supernova. The initial shock breakout ionizes anything in the CSM, and as those high ionization lines recombine, you see a whole slew of lines in the ultraviolet. Something like UVEX is going to be really fantastic for studying these things at early times as we go forward. You can also study the color evolution in the optical. So you might see a supernova that's initially quite red, but then as the shock propagates outward, it destroys some of that pre-existing circumstellar dust. Then you might get to be bluer and then later see the color evolve again to become red if you're starting to form new dust. In the near infrared, so this is like 50 to 200 days, depending on the type of supernova, you can start to see emission from a very warm dust continuum, mostly in K-band. And you can also, importantly for this talk, start to see the near infrared spectroscopic signatures of newly forming dust. So it turns out that carbon monoxide is one of the first molecules that form around 1700 Kelvin, or sorry, a few thousand Kelvin. And once the CO has formed, you can actually cool quite rapidly. It turns out CO is a very important cooling mechanism for supernova ejecta. And once you form those CO molecules, you start to cool rapidly down to about 1700 Kelvin, where you can start to form dust. Into the mid-infrared, which we can probe with JWST, you start to see still warm dust continuum emission. This is now you're seeing the peak of that rather than just the short wavelength tail. You can also start to see dust features like these polycyclic aromatic hydrocarbons, as well as the silicate features, which were so apparent in 2017 EAW models. There's been really great work done on the mid-infrared emission to try to get these dust masses out. 1987A, of course, we have the longest data for. Spitzer Kuiper Airborne Observatory, as well as long, what's the word for it? Submillimeter data, just because it's so nearby. So we have the best dust mass models, but a lot of really great work has been done by Melissa Shabanda at Space Telescope and others like Genevieve to measure these dust masses in a variety of these supernova. But we are very limited in the number of objects that we can get JWST data for. We can only get the most nearby things. These are very faint at these late times. And we also, JWST is hugely oversubscribed. And it tends to be when you are studying things with James Webb, you tend to choose the most exceptional objects. Like all of these supernova are not necessarily typical examples of core collapse supernova. They're exceptional in some way because that's the easiest way to get time on a telescope like JWST. But this is kind of unfortunate. If you want to understand something about supernova dust producers as a population, you really want a more systematic and complete sample. This is where a survey that I've been leading comes in. This is the Red Astronomical Transient Survey, the RAT survey. You guys like my rat? So this is a systematic near-infrared study of ZTF supernova. So ZTF is the discovery engine. There's been a lot of great work in understanding the selection and populations that we're getting out of ZTF. I can do photometric follow-up using the Winter telescope, and then finally get near-infrared spectroscopy using Keck NIRAS. So this is the Keck Science Meeting, but I just want to quickly plug the Winter Telescope, which is on Palomar Observatory. It's a near-infrared, very wide field of view. So what ZTF is about 47 square degrees. This is 1.2 by 1.0 square degrees, which is actually very impressive. Infrared detectors are quite expensive. This is the largest, one of the largest field of view near-infrared surveys. It operates in wide, J, and H short bands, and we've been using it for the last 2 years to get a systematic sample of near-infrared light curves of these supernova. Moving on to Keck NIRAS, which is what I really want to talk about for this is a super awesome instrument. It's very sad that we're losing it. It's really beautiful for doing supernova science because you get both the dust features. So I have here 2 examples of supernova which are showing these dust features. The first is a type 2 supernova, which shows this incredible detection of the first overtone of the CO band head. This is indicating that, yes, the ejecta has now cooled to a few thousand Kelvin, is now getting ready to cool further, and maybe will be, in a couple of years, a very good dust producer. You can also see this warm thermal dust continuum across the near-infrared band in this type 1c supernova, where you just see this is mostly this near-infrared excess is probably emission from warm dust, either some pre-existing shell around the supernova or something that's newly forming. It's not quite clear in this case. Because you also get now the J-band images here, you get a whole bunch of wonderful line diagnostics in the nebular phase of the supernova. These line diagnostics can tell you stuff about the mass of the carbon-oxygen core, can tell you something about the energy of the explosion. These are very sensitive probes of the actual progenitor star and also the supernova itself. So not only do you get the dust emission and features, you also can connect that back to the kinds of progenitor stars that you see. Up to this point, detections of the CO first overtone band head in supernova are fairly rare. There are about a couple dozen in the literature existing. In about 4 nights of data from the RAT survey on Keck NIRAS, we now have 14 detections of CO at a variety of phases here. And including, this is objects that we now have multiple phases for. So unfortunately, we lost some of the late time data for a lot of these non-detections. These were maybe pre-100 days where you might not necessarily expect to see CO formed. But then unfortunately, when we went to go get our 200-day spectra, Keck was broken. But hopefully in a couple of months over the next semester and maybe into next semester, we'll be able to fill out the rest of that late time information and now have a very complete sample of not just CO detections, but also the kinds of supernova that didn't have CO detected. And you can maybe figure out what are the differences between these? Why do these start to form CO earlier than others? Is it correlated with mass, which you can get from the nebular lines and you also see in the near infrared? So I'll just finish with my conclusions. The first is that dust is an essential component of galaxies and forms very early in the universe. If you are forming dust very early, you likely need some kind of massive star to help you along with that rather than the low mass HUB stars, which likely dominate dust production in the local universe. JWST is a fantastic instrument and can probe dust masses for nearby supernova objects. And we should definitely continue to do this, but there are a couple problems, which is JWST is hugely oversubscribed. It's only possible for very nearby objects because you are probing at these very late times when the emission is quite faint. And it's very difficult to obtain a very complete sample where you understand your selection criteria. Be doing systematic surveys in the near infrared from the ground, you're able to sort of overcome some of these limitations. And you can predict this. Should I? Okay, sorry. Yes, so from the ground, you can do more very complete surveys with well-understood selection criteria and be able to get statistical models of the kinds of things you're seeing. And thank you. I'm happy to take any questions.